memory requirements before one should know to design or to come up with a quantum memory. Okay, so when you are preparing something, you should know what you are preparing, what for you are preparing, right? So very, very important thing to know. So as we know, the quantum memories have very stringent requirements because they're so delicate. So the number one is something referred as fidelity. Okay, so what I mean is the information is stored in a quantum memory and retrieved after some time. So that's what the memory is all about. Okay, so one important thing here we should know is what you actually stored, you are actually express like waiting to see the same, right? You expect to see the same, right? You incident something, some information, you see some different information, then in that case you are not satisfied at all, right? Okay, so as we have seen earlier, I think it is being introduced to you people, the quantum information is actually in the superposition form. So this is actually a quantum state. Wait a minute. Okay, let me use my pen notes. Okay, let me take a new note, new drawing. Okay, so for example, as you have seen, a quantum state is alpha 0 plus beta 1. What I can do, I can convert alpha into cos theta by 2, 0 cat, and beta as sine theta by 2, exponential I phi 1 cat. So this is I do to represent geometrically what is this quantum state, right? So if we take a block sphere, right? On the block sphere, you see there is a theta associated with the quantum state, and there is a phi on the equatorial plane. Okay, so this is a quantum state psi is on a block sphere. Okay, all right. So now this same thing is also could be put on a two-dimensional unit circle. What is that is? Okay, you can put on a surface of a sphere a quantum state representation. Also, you can do a circle, unit circle. Let's say on the unit circle, I have 0 cat, I have 1 cat. Okay, right? So I'll have minus of 1 and this is a plus, sorry, plus of 0, sorry, minus of 0. Okay, fine. So let's say initially the atom is represented by this vector sign. Okay, right? There is a specific angle between 0 to 1 theta. Okay, fixed angle is there, and that, okay, let me take some different angle to avoid the confusion. So let's say some theta and phi I used, let me use some delta. Okay, between 0 and 1 some delta is there. Now remember, you are starting a quantum state or just to store the quantum state at this weights alpha and beta. Okay, after some time it is slightly tilted, maybe because of the environment. So the theta gone on, so delta gone on to become delta prime. So there is a small variation is fine, it's accepted. Okay, but if the a delta becomes all the way very, very different, let's say like this, so delta to go on to become some delta prime, which is having a lot of difference. In that case, I would say the quantum state which we stored has actually become some unacceptable quantum state. Remember, that's still a quantum state, but it has gone out of range, right? So that is what people call the fidelity, the actualness of the system is gone to lose. Okay, so I would say the fidelity there would be something around some 75%. Okay, if slight change in delta, we can say fidelity is something like 99.5%. So if that is there, 99.5% of the actual information is intact. If I'm able to retrieve back, then I would say fidelity is very high, especially for quantum computing. A very good fidelity is actually required. Okay, why it is required? It is going to ensure the coherence in the system. Okay, it is going to ensure the existence of superposition for a longer time. Okay, because some of the atoms goes out of order. It is like there are 10 dancers on a stage which who are dancing in sync. It looks very appealing. The moment somebody in the middle or somewhere here and there, two of them goes out of sync, in that case the dance looks very odd, and you usually say, oh, it's not appealing at all. So that is what, to have this coherence in the entire systems which we are talking into, bringing into the consideration to do the quantum computation. If if some of the guys goes out of the order, then you would say the entire information is losing its fidelity. Okay, right? So coming back to here, one of the requirement is the memory should have very good fidelity. Means it should able to store, that's for sure, but it should also be able to retrieve the same quantum state in a same identical form what was given in the initial place. Okay, and the next one is long storage time. Means long coherence time we just saw earlier. Okay, so there must be a scenario where a quantum states should have a long enough time existence so that I can use that for the communication. Okay, let's say I create a qubit and I send it to other place. By the time it reaches to other place, if it loses this qubitness or the quantumness, there is no point in sending it, right? Okay, so that is the long storage time our memory should have. Okay, so required range I have specified here something like a milliseconds to seconds, or more if it is possible, then it's very good. Okay, so 100% coherence time is very perfect quantum system. Okay, 78% coherent is like slightly decoherence, right? So okay, compared to the fidelity, these things here in this case, these numbers are slightly fine. But in the case of 37% coherent, means systems going crazy out of order in the lifetime, coherence lifetime. In that case, it's like out of 10 dancers, something like 6 7 people are dancing with irregular way, and only 4 are fine. So in that case, the entire dancing would look very crazy, not at all appealing. Okay, right? So that is a couple of quantum memory requirements. Let's go and see, is there any other requirements we have to bother? Okay, right? So another thing is, when you give the information to the system, okay, let's say it stores, and it when I try to retrieve, it should respond in much quicker fashion. There should be on demand retrieval. Okay, there should not be lag, there should not be time between I demand the information, system giving the information. Okay, so that is what on demand retrieval is very important. So this is required for synchronizing the operations in quantum networks. Okay, right? So by the way, quantum systems are, compared to the classical case, this definitely have no lag whatsoever. But still, between each memory to other memory, there should be a synchronization. So that means they should respond in same way, so that we will retrieve and connect them and have a good quantum networks. Okay, on-demand retrieval is one of the requirement. Okay, and the efficiency of the quantum memory is it should be able to store and retrieve efficiency with 100%, close to 100 at least, and losses, if there is any losses, that would reduce the entanglement distribution rates and the scalability connecting the system to a larger entity, that also being affected if there is any loss in the efficiency of storing the information. Okay, right? And let's say if I just take a physical memory, I'm not talking about one single memory. Let's say I'm taking a scheme of various memories inside. If I take that, it should be able to, or it should allow me to store many qubits in it. Okay, multiple, or for example, a photonic based chip is there. I should be able to store many multiple photons in the system. Okay, so it's not like specific few only. If it is allows, then my job of having quantum memory and quantum computation is not not satisfied. Okay, so a multi-mode capacity is also very important in the case of quantum memory. Okay, and for example, there is a there is a material or solid state memory. If I have one more memory at another point, I have to communicate between them through using something called flying qubits of photons. Okay, so this solid state memories or this hardware memories must be connectable between each other with some flying qubits. That means the compatibility should also be there. Otherwise, see, with few quantum memories you can't do, because quantum memory is so time wise very limited. So that means you have to have some kind of a distributed network. Means there should be a connection means through photons. Those photons should be able to reach out to this quantum memory and exchange the information. That means that kind of a compatibility is also going to make a very crucial uh, factor. Okay, right? So let's see what else I have. Okay, uh, preservation of entanglement. Okay, right? Quantum memory should allow more entangled states without degrading the correlations. Basically, remember, entanglement is nothing but, okay, entanglement is nothing but creation of, let's say, there is a system A and there is a system B, right? There are two systems. If there's some kind of a correlation I'm going to create between them, some kind of a relation, okay, so that relation, if I represent as a quantum state, okay, quantum state entangled 1 2, like a 0 0 plus 1 1 is a bell pair I'm writing. Okay, right? So which means if I try to make an observation on system A, if it falls to 0, the second one is also forced to falls to 0. This is what the entanglement probability is being introduced to you already. So quantum memories, if I have a quantum memories, if I create entanglement between quantum memories, they should preserve this entanglement. They should not spoil this entanglement. Why? Because this is very much required for something called quantum repeaters, which we'll discuss after this part. Okay, so preservation of entanglement is one of the factor need to be considered while designing or devising a quantum memory. Okay, and the next one is scalability and integrability. Okay, so should be realized in the system, these two things, so that we can do a scaling and integration. Okay, so why quantum processors or photonic circuits are the ones which are actually allows one to improve or scale the systems to larger computations. Okay, so quantum memory should allow this. Okay, a practical quantum memory needs to be faithful overall and efficient and long-lived memory, And on-demand retrieval information, you should allow a multi-mode information storage. Okay, it should be compatible to the flying qubits. It should be entangled preserving and scalable. So these are like the summary of the factors which needs to be considered when I'm going to design a quantum memory. Okay, right? So let's see what else I have. Okay, fine. We have seen all of them. Remember one thing: you can't ensure all of them to be satisfied with perfect manner. Okay, there is always, if you choose one to have high, in another case you would lose that. Okay, another factor you would be losing all the way. So this is what is actually summarized here. There is a performance trade-offs one has to do. Why? Let's say I have a long lifetime. If I want to have a long lifetime, so there will be a lower efficiency in the system. Okay, right? If I want to have a high fidelity, okay, high fidelity means what? The system should able to store the information intact and retrieve the same information. Means, okay, high fidelity. Let's say high isolation, highly isolated system. Okay, what it ensures? Okay, isolated system, if you just take, if I give a quantum state, since it is completely isolated from the environment, only I'm talking to that, it is talking to my photon, it gives the same photon as it is. But remember, it's just like I'm just putting the money and taking the money from, let's say, some kind of a bank locker. But I'm not doing anything with that, just for the sake of taking, putting the money and just taking. I'm not processing it, I'm not using it. So in that case, there is no use with that kind of a thing. But if there is a possibility to process the information by using some other means the system is open for external interaction in a very controlled manner. In that case, I can create the computation part. Computation is possible if the system is slightly open to the interaction. Okay, so that means there is a possibility when I open the window in one place, there is a chance of somebody, imposter, would go through the window and spoil the environment and create some noise. But the trade-off one has to do, because I have to interact with the system. The input signal has to go and interact. So that means you have to have some kind of a trade-off. What is the trade-off? Is let the system to environment interact with the very controlled manner with the environment, so that I can talk to the system. At the same time, I could just ensure I would reach the fidelity levels, let's say 100 to 99 range. If the fidelity is there, that's fine, because the system has to interact. Okay, and see, let's say there's a multi-mode storage. If the system is allowed to do so, in that case, so many, so like in individual memories are there, they just interact with each other. So there is going to be like a more complex system is going to be created. Okay, so you can't be too greedy to put so much of quantum memory together connected just to have more memory, more computation. The moment you do that, system becomes more complex and this also becomes more prone to errors. So in that way, the actual purpose of doing computation is lost. So again, there should be a balance between the complexity and also multimodal storage. Okay, so these are the some of the factors kept in the consideration, and one has to design a quantum memory. Then only you will have a perfect quantum computation. Okay, so let's see what are the various phenomenal platforms one can use to realize quantum memories. Okay, I've listed here more or less all the existing memories are actually covered over here. Okay, so one is something called atomic ensembles, right? It's like a collection of various atoms people call atomic vapor. Rubidium and cesium are the main uh, the right rubidium and cesium are the atoms which were taken to realize these atomic ensembles. Okay, and the next one is called rare earth ion doped crystals. Okay, why rare earth ion doped crystals? Because this rare earth ions are going to have a very long coherence time, so that's why people choose that, even though they're rarely available. They're like erbium, yttrium. These are there in the periodic table at the very corner. So these things are a very good entities to realize a long coherence qubits. We will discuss slightly in detail what are these. Okay, and single atoms and ions. Okay, and atoms I take, I can ionize them and trap them between the electromagnetic fields. Let's say electrodes, I can trap between the electrodes and use magnetic fields to control their motion and movement. And I can have, based on their position, I can create a qubits out of it, or based on their magnetization magnetization values, also I can create some kind of a qubit. So there are so many techniques people use for single atoms or ions to create the qubits out of it. Okay, and the other one, another solid state quantum memories are actually realized out of something called nitrogen vacancy centers. Okay, they're called NV centers in short. And similarly, inside the silicon material, you can create vacancies, and that is actually called silicon vacancies. These are like solid state quantum memories. So they would allow you to do a quantum information storage and retrieval. We'll discuss slightly one by one. Okay. And the photonic memories, we just saw already. Photons are the flying qubits. So in fact, photons travel along with a memory stored in the form of their polarization. So that also we'll just slightly discuss. And at the end, the mostly used quantum memory is something called artificial atoms. They're known by name called transmons. Okay, so they're simple electronic LCR circuit resonators. They are actually mimics the nature of atoms. We'll see that also in detail little bit. Okay, fine. So first, let's understand what is atomic ensemble based quantum memories are. Okay, so let me use next slide. Yeah. So using atomic ensembles, I can have collective excitation and a long coherence time based quantum memory. So how it is done is something called using the phenomena called electromagnetically induced transparency. Okay, so let me use atomic three-level atomic structure. Okay, so if you see on the right, please concentrate on the right side. What you see is there are three figures. Okay, so in each figure there is a 1 2 3 written, 1 ket, 2 ket and 3 ket is written. Okay, so let's just concentrate on the right extreme where a ladder is mentioned. Just say ladder is mentioned. Basically, what I mean by that is there is a three-level atomic system, okay, where states or orbits are arranged in ladder fashion, one next to two and the three. Okay, now I can choose. If the electron is in the ground state, I can choose the electron to move to the state 2 by supplying a photon of angular frequency omega p, which matches with an energy exactly with the separation of level 1 and 2. In that case, electron may jump to ground to excited. Okay, right? Now, fine. Let's say if I put the omega p very close to 3 and 2, in between 2 and 3, in that case the pump field, sorry, in that case the probe field omega p stands for probe field. The probe field is very close to shifting the electron from ground all the way 1 to 3. So a slight variation in the energy separation is fine actually. In that case, the electron can jump from all the way to 1 and 3. Okay, right? So, right, let me use my hand note so that I can explain a little bit better. Okay. Just a minute. Yeah. So I'm just trying to explain what is EIT, electromagnetic induced transparency, electromagnetic induced or electromagnetically induced transparency. I'm just taking 3-level atomic system, 1, 2, and 3. Okay. So just I'll extend this for my comfortability in the explanation. It's like, okay, 3-level atomic system. Now, by the time, let's say now, I can have a probe field which is very close to 1 and 3. Okay, probe field 1 and 3. So what I mean is, I'm just exaggerating. This probe field omega p can put this electron even in the excited state. It is slightly detuned, means slightly mistuned. So there is a separation, a change of this much. I'm sorry. Okay, right? Now, the omega p is there, which can shift the electron from ground to excited. Okay, so this omega p field, which is say omega p is coming, which is easily gets absorbed by this kind of a medium. But I don't want that to happen. Okay, what I will do, I can put a very strong coupling field, very strong coupling field between 2 and 3, which is represented by angular frequency omega c. Okay, a coupling field. So what this coupling field does, or a coupling incident light does is, if at all if there is an electron is there in the excited state, it forces that to come to level 2. Okay, so the strength of omega c is so much, there is no chance the electron can exist in the excited state in the presence of omega c. If something is there, it immediately pushes back to the 2. That is its role. So that is a classical way of understanding what is happening here. But in the case of quantum wave, what is happening is there's a path. See, there are multiple paths electron can reach from 1 to 3. So what are those multiple paths is, let's say one path is it can go directly to 2, and from 2 to 3 it can go by utilizing omega p and omega c. Okay, this is one path. So another path is it can go observe omega p, go to omega 3 with omega c, come down by emitting omega c, again it can go to omega observing by omega c, it will go to 3. Okay, so basically what I'm showing is it can just do one straight up, or it come down and then go to straight up. Okay, so these are like paths, various paths. Okay, so and one more also is there. What is that is, it can go and come down and then go up and then come down and go up. Okay, so these are various possibilities. You can say possibility 1 plus possibility 2 plus possibility 3. So there are so many such possibilities, which are electron can jump to 2, and because of the strong field, it does various oscillations between 2 and 3 and reach to 3 level. Okay, And now remember, this is actually combination of various paths. Because of this various paths, there is something called quantum interference takes place. Quantum interference. Okay. It is also known by name quantum coherence. Okay. Because of this, what happens? The chance of photon being observed by omega p light, okay, and chance of electron being existing on level 3 never going to happen, because by the time electron is there in the level 3, it is pushed down to 2. Okay, so that means most of the time electron is actually not present in the state. Okay, right, not presence in the state 3, it is always at the state 2. So I'm forcing the absorption, a chance of absorption of omega p is actually suppressed. That is the figure given here. See the right side corner, the dotted line, the interaction between 1 to 3 is actually crossed. Okay, so that chance of absorption is not there. So on the left you see there is a absorption curve with a dotted line. If the coupling field is not there, the absorption would takes electron would jump from 1 to 3. That absorption will be there for that particular light. If not, if the coupling field is switched on, in that case, exactly wherever there is a absorption was taking place, the light is being absorbed. In that frequency, I'll have a dip. Dip means that light is no more absorbed. Okay, right? So what I can do, if if we just go back to the quantum optics and see, there is a chance of I can induce electromagnetically induced transparency in the system by just incidenting two lasers. What I mean is, if there are two laser lights, okay, so very interesting thing I can tell you now. Let's say there is some material, okay, some solid material is there. Let's say I incident, let's say omega p light with omega p frequency. Let's say it hit at point and it just transmits without, probably just like a glass. The moment I take a very strong coupling field, exactly hits at same spot, which is omega c. In that case, what happens? Okay, suddenly this omega p is no more observed. Okay, right? Sorry, it is other way around. Let's say, okay, let me remove. It's other way around. Let's say there is a field, right? Initially, there is a field which is incident. It is observed and consumed by the system. And now, the moment I just incident omega c, in that case, what happens? Both light gets transmitted as if nothing is happened. Omega c, omega p. What I mean is, the omega p become transparent to the system the moment I switch on coupling field. So the material is becoming transparent to the system. So in this way, what I can do, I can use this effect to create a storage of light in the system. Okay, so the storage of the light in the system is done based on looking at the refractive index of the system. From there, people usually do what they do is, in this kind of a material, you can slow down the group velocity. Okay, it's another concept, group velocity of the light, okay, propagating through the medium. Okay, right? So you can slow down so much, okay, you can slow down so much that it appears to be a photons coming in into the material. This electromagnetic induced transparency kind of a material. So the light gets stuck inside for a few microseconds and then comes out. So the time when it stores inside this material, which is actually called like let's say memory, is being realized out of it. Okay, so just like I see, initially I'll switch on omega C. From time being, the photons gets inside and stays there for some time. Okay, the moment if I don't have omega C, the light is transmitted. When I have omega C, light okay, when I have omega C, light get transmitted. When I don't have, light doesn't get transmitted. Okay, so using this, like, if for a naked eye, if I perform this experiment, I don't see the difference. But if you do it with the uttermost care with the quantum optics experimental lab, what you see is light is being trapped for a few microseconds inside the material that is being used as a quantum memory. Okay, EIT based quantum memory. Okay, fine. So the other way, other kind of thing is something called Raman based Raman Raman. What's the name? Raman memories they call. Okay, Raman memory. As you guys know, the Raman has given Stokes and anti-Stokes. Okay, so this is again based on three-level atomic system. What is that is? Okay, let's say you incident energy onto the system. Let's say three-level atomic system is there. The let's say electron gone to level 0 to 1. Okay, and it stays there for some time and then comes down to, instead of coming down to 0, it comes down to 2 by emitting lower energy. So let's say you send 100 joules of energy, it emits, let's say, 60 joules of energy, and remaining 40 joules separation is kept inside the system, or it may be emitted by the system in the form of heat or anything, but some part of energy is inside. So that could be used to store the information. Okay, and this is one more possibility is, let's say the system is already in some higher energy state. Okay, again here it is exactly opposite to that. So system is already here. When I send a photon of this much energy, let's say something like some 70 joules. So by taking, the electron goes up to the level 2 and jumps back to the all the way to the ground state 0. So and it emits, let's say, some 90 joules of photon, which is very much different from what I have given in the initial phase. So I'm getting large amount of energy from the system. So you can think in the case, in this case, some kind of a enhancement of incident energy is taken place from the system which is already in the excited state. So these are actually called Stokes and anti-Stokes phenomena. Okay, so using this phenomena, one can realize a quantum memory. So this is actually possible with atomic ensembles. So that is what atomic ensemble based quantum memories are. Okay, right? So what else other memories which we could think of is rare earth ion doped materials. Okay, so what these things are: rare earth, rare earth ion doped materials. Okay, so they take this rare earth ions, they dope with some other rare earth materials. They take yttrium host, erbium dopants they will put in yttrium. Okay, erbium. So this kind of a material they take and they dope inside. So what happens, because of the presence of this dopants, right? So inside the material, let's say inside there are dopants are there. Okay, there is a host. Okay, by nature, right, these things must absorb the incident light, okay, in some fashion. But what happens because of this dopants inside, okay, if I try to see the absorption pattern of the light, okay, so there is a very large window of light frequency. If I send into this, so what I see because of this kind of a material, okay, so there is a absorption is not continuous. What I see, there is a absorption is in a particular manner. So absorption is possible with, let's say, omega 1 frequency and omega 2 frequency, omega 3 frequency, omega 4 frequency, omega 5 frequency. Okay, basically it's in very discrete fashion. Omega 6, omega 7. What you see is, instead of light being observed continuously for all the frequencies, but if a light is incident in a very broad fashion, if the omega, all possible omegas are there, but it is only being observed with certain single frequencies around. So this is actually creating something called atoms in ion form, creating some kind of a Coombe kind of absorption. They're calling them as atomic frequency Coombe, just like a Coombe, you see. So this is absorption versus frequency. Okay, I have all the frequencies. The window is, let's say, the window of frequencies, for example, let's say for here, let's say some 100 hertz to, let's say, some 1000 hertz. Okay, but only within that, only at omega 1, let's say 200 hertz, 300 hertz, 400 hertz, 500 hertz, 600, 700, 800, only between those hertz only the light is being observed, not in other case. I don't see 150 hertz frequency is being observed. Okay, if such a peak absorption kind of a comb is created in a material, okay, what happens now? Very interesting thing would takes place. Let's say I have a pulse of photon. Okay, pulse of photons are there. This is a, let's say, pulse. We have seen already pulse. So the pulse could have, pulse means what? It has a two signals brought together. I create a pulse. Okay, so if I have such a pulse, okay, that pulse will have so many frequencies, right? If I choose a pulse in such a way, remember, the pulse is incident onto this frequency comb. Okay, let me draw now a single lines. Okay, if this goes and incident onto this material, okay, this pulse of photons, okay, if it is incident onto this material, now interestingly this entire pulse may not be observed. A part of this pulse are observed, right? Most of the part of this pulse is observed. Okay, it is observed. And see, obviously this, wherever there is a electrons which is atoms are observing at these frequencies, they observe and they emit after some time. Okay, because they don't have a lifetime absorption. So after some time, what they do, let's say there is a pulse is this observed, let's say at time t0, okay, and some part of the light is being observed, let's say. After some time, let's say after some time t, the same pulse or somewhere very close to the pulse is emitted. Okay, so there is a time delay between absorption and emission. Okay, because this frequency cone, this emission is actually also called echo, photon echo. Okay, so this is incident signal and echo signal. So there is a time delay. That time delay could be used to create a memory. So within that time delay, you can do lots of computation. Okay, quantum computation. So that is how atomic frequency groups are being used to create quantum memory. Okay, so I happened to work in the lab which is doing this experiment in Sweden. So they were using atomic frequency groups of rare earth ions. They were realizing quantum memory to enhance the interaction between incident light, incident pulse with the atomic frequency group. You can just add some kind of a cavity mechanism. So that is where I actually contributed in creating a mathematical model how a cavity is going to either going to add some advantage of having better interaction and better quantum memory or not. That is actually I worked during my postdoctoral study in Sweden. Okay, so that is a atomic frequency comb for you. So what is the other thing is solid state defects. Ions we already just discussed. Okay, there is something called NV centers. Okay, so what is the NV centers are nitrogen vacancy centers. Okay, so I have 5 minutes. We'll finish photonic memories and transmons and NV centers in next to 5 to 10 minutes, and then we'll take a break and we'll come back. Okay. So let's talk about NV center memories. Okay. So what I mean is, if you just take a diamond, okay, right? Diamond, if you just take a material, okay. So inside a diamond, everything is all about carbon. Okay. So carbon, 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 well connected carbon. So I'm just exaggerated diagramming. Okay. Now, what happens? I knock a couple of carbons and replace one of the carbon with nitrogen. Other one, you just leave it as it is. You leave the vacant space. By the way, a vacant space becomes a positive, and N which is coming in becomes a negative. So it is just like a positive charge and negative charge separated by a distance. So if the charges are of equal, positive and negative, it is going to create an electric dipole. Okay. And this dipole is very, very sensitive to the external environment. Okay. And people started using this electric dipole to see the presence of external environment fields. For example, there is external magnetic field is there. What is the effect of that external magnetic field on this? What is the effect of any, let's say, even minute change in the external magnetic field would actually cause the nature of this particular NV center. How it happens is, for example, if you just to try to draw atomic structure of this particular NV center, let's say it will have some ground state and excited state. Okay, when the presence of external magnetic field is there, in that case, what happens? The ground state is split to two halves. Okay, two sub levels. Even the excited state also split to two sub levels. Okay, let's say if this is 0, this would be 0 minus and this would be 0 plus. Okay, now the ground state electrons which were there could be either here or here, we don't know, right? So let's say the electrons are here at the top level. In that case, if the light is incident of energy strength between this two, 1 minus and 1 plus, in that case, only electrons in the 0 plus state would excite, right? Electrons in the 1 0 minus state would never excite. So what one can do is, instead of having electrons in a particular state, where people start with electrons in the 0 state, and then the moment there is a start of external magnetic field, the split would happen, this uh, Zeeman shift, okay, the ground state. So electron would move on to either 0 minus or 0 plus. when the incident light is exactly suits this energy separation, in that case only I will see absorption, otherwise no absorption at all. Right? Right? So using this, people can use this mechanism to measure external magnetic field. At the same time, you can realize two superposition states out of this system and create a memory out of it. Okay, so that is a NV center memory. Other one is NV center memory. Other one is the silicon frequencies also more or less work in the same way. A photonic memories are something like, say, photon means a light which is coming. It has a polarization in a particular direction, right? So the electric field oscillates in a particular direction. Let's say this is a vertical polarization. I can rotate this polarization by slight angle by having, let's say, quarter wave plate. Okay, so which means the quantum state starting in a vertical polarization would go on to become a superposition of horizontal and vertical polarization. Okay, some here I have just a quarter wave plate or something. I use some kind of a rotating effect for the polarization. I can create this. Okay, so I created a quantum memory out of the system. The photons are carrying of quantum memory. Okay, so once they go and interact with some kind of atoms, they may transfer that quantum memory to the atom which is in the ground in the first place. The moment this photon goes and interact, it might put the electron into the superposition state. In that way, the quantum memory is transferred. Okay, right? So that is a photonic memory for you. Okay. The next one is transmodes. Transmodes. So what are transmodes are? Okay, if you just take a LCR circuit, there is an inductor, there is a capacitor, there is an internal resistance. You connect to a battery. What happens is the capacitor can get charged up in a various fashions. Let's say it can charge between 5 coulomb, 10 coulomb, and 15 coulomb, and 20 coulomb. So there is some kind of a quantum states exist for charging of a capacitor. So you see between each state, the separation is always fixed. Okay, the 5 coulomb separation, 5 coulomb separation, 5 coulomb separation. Okay, basically if you just take a atom and its electron orbit states, you see as you go further and further, the orbit comes very close. Okay, as if there is a continuous banks of orbits are there, so the separation is actually unequal. Okay, so very as you go away from the nucleus, the separation between orbits becomes very small. There is a non-linear separation. It is just like a ground state and excited state and the next excited state and the next excited state and very close excited states. This is what actually the real atom would look like: 0, 1, 2, and 3, and so on. This is non-linear energy separation. Okay, in the real atom, natural atom. Okay, but in a case of LCR circuit, you see energy separations are very equal. Okay, so from the no separation, let's say, okay, 5, 10, okay, this is 25, 5 coulomb. Okay, so so here, is it possible to have unequal separation in the charged states of the capacitor? Is possible. The question answer is yes. So you replace the inductor with Josephson junction, where one is superconductor, there is an insulator, there is again superconductor, and then let's have a capacitor and the internal resistance. And instead of connecting to a battery, so you incident a radio frequency signal. Okay, that acts like a in energy supplier for this LCR circuit. In that case, the entire setup is actually going to have a, let's say, in terms of capacitor being charged, if you're going to find what are the states of a capacitor, you would see there is, let's say, 10 coulomb charge, 20 coulomb charge. The next one is, let's say, 25. Next one is 28. Okay. Next one is, let's say, 29. So it's unequally spaced. The energy separation or the charge separation is unequally spaced. It is decreasing in a continuous manner. So the moment you add a Josephson junction in place of inductor, this is what happening. The question is why they will add a Josephson junction, JJ junction, Josephson junction, because Josephson junction is actually a superconductor and there is an insulator, there is a superconductor. Okay, when you cool this superconductor to millikelvin, let's say 50 millikelvin, so there is a formation of Cooper pairs. Electrons forms a Cooper pair. These electrons even tunnel through the insulator. Since they can't stay in one part of the superconducting surface of material, they just go back and forth. They create some kind of a frequency of oscillations. These frequency of oscillations would create some kind of a energy, like so states, energy states, energy state existence, that is indirectly going to influence this capacitor, and its capaciting status, charge status would become unequal. So in this way, then we'll have a chance of storage of information onto this LCR circuit between any two fixed charge states. Let's say I can take them and create a 0 ket and 1 ket. So this is what being people using from quite some time. Okay, so all the IBM, most of the IBM, like all the IBM quantum computers are based on this. In India also, recently coming up quantum QPI Bangalore, they are also working on this, and their computers also based on this transmos. Okay, so we'll just stop at this point for 5 minutes, and then we'll get back and start the quantum memories. So it's 12, sorry, 4 8. We'll start 4 9. We'll start at 4 4:15. Yeah, somebody was asking what is the book to study. Yeah, well, there's a question: what type of material execute EIT based memory? So these are like called non-linear